Okay, so this is a review of some homework that relates mainly to infinite sets, though this first one does not. It's just a regular function problem. And the last one in this set is a problem relating to induction. Okay, so this first one says, consider the function f from the set A to the set B. And you're told that A is identical to the null set and B is not identical to the null set. So A has no elements and B has some unspecified number of elements. Now you might think this is a trick question because you might have reasonably assumed that a function, because of the demands we place on the nature of functions, must be defined on sets that are not empty. But that is not the case. There is nothing in the definition of a function that says that the sets that it's defined on have to have elements. If A and B are actually both identical to the null set, then that's actually called the empty function. And there's nothing particularly useful about it, or this one, except that it gives you a chance to test your ability to prove things like this without visualizing arrows, which means you have to just appeal strictly to the definitions of injective and surjective, right? So the important thing to understand is that both injective and surjective have definitions that are conditional in nature, and so you just need to use your understanding of the truth conditions of the material conditional to get these right. So for example, with injection, you know that a function is injective if and only if f of A equals f of B, then A is identical to B. And now, of course, you've been told that A is identical to the null set, and so that tells you something about whether anything satisfies the conditions of being in the range of F. Remember, the range is different than the codomain. B, right, might be the codomain that has some elements, but that doesn't mean the range has anything in it. So just think like that, and you'll get both these pretty straightforwardly. Okay, this number 2 is stated a little bit awkwardly, right? But what this means is you're considering a function from z plus cross z plus, which is a Cartesian product on all of the positive integers, to q plus, which is all of the positive rational numbers. So the function takes the ordered pair xy, which is what you're going to get when you're thinking about a Cartesian product, to the ratio or fraction x over y. So again, you just need to figure out whether it's injective and whether it's surjective. And so for injective, okay, just again applying the definition which we wrote above, right? You're just going to have to ask yourself if F maps every ordered pair into one and only one value of q plus. And then when you think about surjective, you're going to be asking whether there is any positive rational number that is not mapped into by some ordered pair of positive integers. Now you'll prove your result in exactly the same way by simply appealing to the definition of injection and surjection. Number 3 says, prove that a fully occupied Hilbert's hotel can immediately accommodate a set of guests of cardinality Aleph null without evicting any current guests. So if you've been through the lecture and the reading, you know that Hilbert's hotel is simply an infinitely large hotel that has no vacancy. And the example we considered in the lecture is the idea that even though the hotel has no vacancy, it's always possible to create a vacancy without kicking anybody out. And you do that by just defining a function, and the function for that particular one is just f of x equals x plus 1, right? So what that does is it takes the occupant in the first room and just moves him to room 2, occupant in room 2 to room 3, and that creates one extra space, namely the very first room. So now you're asked to do something similar, but this isn't the function that's going to do it. This only creates one space. You could create an indefinite number of spaces by letting this function run for an indefinite amount of time, creating one space after another. But what we're asking for is an application where we immediately get an infinite number of spaces, and specifically infinity related to, that is, has the cardinality of Aleph null, which is the cardinality of the positive integers or natural numbers. Integers too, for that matter, not just positive integers. So this is actually simple. It's not some complicated function. Just think of an f of x that will immediately create an infinite number of spaces. And if you're having trouble thinking of a function like that, just go back to the lecture and review where we are talking about how there are so many different infinite subsets of the positive integers, and not just subsets, but proper subsets of the positive integers that can still be put into one-to-one correspondence with the positive integers. And that connects nicely actually to the next problem, which is really just to see if you've been paying attention to the lecture. Here you're asked, is it true that for any sets A and B, if A is a proper subset of B, then the cardinality of B is greater than the cardinality of A? And that is actually answered in precisely that part of the lecture that I just referred to. So this next one says, suppose that A and B are sets and there's a surjective function from A to B. If A is countable, does it follow that B is countable? So even though this is a question that is not simply about finite sets, but encompasses infinite sets as well, you can easily get an idea for how you would approach this by just, again, visualizing a finite surjection, right? So, of course, a bijection is a surjection, but we don't want to focus on that. So if we think about the classical characterization of a surjection, it's going to look something like this, right? So every element of B is mapped into by an element of A, but with the surjection, it's also possible that multiple elements of A are mapped into the same element of B. Okay, so then the main thing you're going to observe here is that with a surjection, it's either going to be a bijection or there's going to be some subset of A they call it C, where f of C to B is a bijection. Now we're looking at finite sets here, and of course when we make the subset of A, C, it's clear that in finite terms, A has a smaller cardinality, C has a smaller cardinality than A. But now when you extend your thinking to the infinite, it's not going to follow that C has a smaller cardinality than A, but it still will follow that C is smaller or equal in cardinality to A. And that means that there's a set that's less than or equal in cardinality to A, for which there's a bijection from A to B. And that pretty much gives you all the pieces of the puzzle. Okay, number 6 is about the Schroeder-Bernstein theorem, and you'll want to go back to the lecture or the book or both to make sure you understand what the Schroeder-Bernstein theorem says, but it's really a power tool. And it tells you that if you have two sets, A and B, whether finite or infinite, but this really is most important and useful for infinite sets, that if you have an injection from A to B and an injection from B to A, then they have the same cardinality. That seems intuitively obvious, but it's not particularly straightforward to prove. But when you draw yourself a picture, right, you might draw your standard picture of an injection from A to B. So it might look like this, right, leaving open the possibility that there are elements of B that are not mapped into. So there's an injection from A to B. What about also an injection from B to A? Well, we could draw it as a composition. And of course, to have an injection from B to A, then that's actually going to demand that A have at least as many elements as B, right? So that's the only way we get an injection, is if we get a bijection, which means we have to go back here and add 1 into A. Okay, so we can use this theorem to show things that would be very difficult to show without it. And sorry, I was just drawing this picture on the wrong problem. It's okay, we'll just go back to the right problem now. So when we're asked to determine whether the open interval from 0 to 1 is, and remember that means not including 0, 1, has the same cardinality as the closed interval 0, 1, which does include 0, 1. And remember here, we're specifically talking about the real numbers when we are talking about this interval. Obviously, there's nothing in between 0, 1 if we're talking about the integers, and although if we were only talking about the rationals, there would be, but we're talking about the real numbers here. So it's often very difficult to demonstrate there's a bijection between infinite collections of real numbers, but it's not so hard to show that there's an injection in one direction and an injection in the other. And if you can, the Schroeder-Bernstein theorem tells us that if you do that, then you've demonstrated that they have the same cardinality. So that makes it a really simple problem. So going in one direction, specifically from left to right, is very simple. And in fact, the solution in the example considered in lecture is the same as the solution to this. Going in the other direction, from the closed interval 0, 1 to the open interval, requires just a little bit more thought. because now you have 1 and 0, which are not in the open interval. So you can't just, for example, use f of x equals x. You just have to come up with some f of x that maps 1, 0, and everything in between into the open interval 0, 1. And if you think about that for a little while, you'll realize that the best way to do that is with a function that involves some kind of fraction. So this next one, number 7, says define sets A and B so that both sets are uncountably infinite, but A intersect B is countably infinite. Now that's something that you should grind on for a while, but the key to doing this is going to be to realize that we have different ways of naming sets, right? We have power sets, we have intersections, we have unions, and so you can take the intersection of a set that's defined in more complicated ways. So you should try to solve it with just that much information. I think that should be enough. But if you are still having trouble, come back and let me tell you just a little bit more here. So suppose, not thinking specifically about this problem or this A and this B, but suppose I said, sort of abstractly, that we have a set that's like, I'm going to define as A union B, right? And I'm going to intersect that with, say, A union C. Okay, well, you know that the intersect of A union B and the A union C is just A. So if A had specific properties and B and C had specific properties, then essentially when you put these together, the properties associated with B and C drop out, and all that you're left with is the properties associated with A. Okay, so 8 and 9 are a little less straightforward, though they seem, when you look at them, to be sort of obvious, and it's frustrating that they're not easy to prove. So 8 says, prove that if A and B are sets and the cardinality of A is identical to the cardinality of B, then the cardinality of the power set of A is identical to the cardinality of the power set of B. Now, if you just think about finite sets, it's just obvious this is correct, but we're kind of in Zeno land. We start with small sets, we do it on larger sets, and we just say, well, clearly, if you keep doing this, you're going to get the same result, but that's just not at all obvious. Now, you don't actually have to use induction to do this. This is not an inductive problem, but you still have to have some kind of insight into how to think about the relation between these sets and functions. So one way to do it is just to actually draw out the relation between a function on the original sets A and B and a function on the power sets, and what the names of those would actually sort of look like. So if we have sets A and B and a function from A to B, and because we know that A and B have the same cardinality, we can say that this function is a bijection. And if it's a bijection, it's going to look something like this. If we just populate it with a small number of entities, if you put A and B in A, then just by definition, there's going to be an f of A and an f of B in B, and that's it, because it's a bijection. And so again, simply because we've defined A and B as having only two entities, we can roster out the power set of A, right? So the power set of A is just the set of all the subsets of A. So that's going to be the null set, the set that contains A, and the set that contains B, and the set that contains A and B. And by the same reasoning, right, we have B, so we have it, f of A and f of B are the constituents of B, and so the power set of B is going to look like this: the null set, the set that contains f of A, the set that contains f of B. That's actually missing a little bracket there. And the set that contains f of A and f of B. Now this, of course, is just a very simple example, but we're being asked to demonstrate a relationship between the power set of A and the power set of B, specifically that the power set of A has the same cardinality as the power set of B. And to do that, we're going to want to come up with a way of characterizing G that captures the relationship that we see in F, or that embodies it somehow. So you could ask yourself, what does G equal to from a set theoretic point of view? In other words, actually, what does G of X come out to be in terms of the set that it creates? Obviously, it creates the power set of B. It creates that. So if the bijection we're considering is mapping the null set to the null set, the set that contains A to the set that contains f of A, etc., then we notice that, say, G of the set that contains A is the set that contains. So where X is identical to the set that contains, G of X is going to be the set of all f of Y. And why do we say f of Y, right? Well, because f of A, right, is the element of that set. So G equals X, G of X equals the set of all f of Y, such that Y itself, which in this case A, is an element of X. Right, so G of X equals the set of all Fy such that Y is an element of X. And that works if we think of X equals the set AB, right? That's going to map, G is going to map that onto the set that contains f of A and f. So G of AB equals the set of all f of Y, in this case f of A and f of B, such that A and B are members of X. So you're going to want to use this insight into the nature of G in order to prove that G is a surjection and that it's also an injection. So you know what that amounts to. That amounts to using those definitions. So in this case, because we're talking about the power sets of A and the power set of B, then for an injection, right, you're going to need to show that if G of X equals G of Y, then X has to equal Y. And then for a surjection, you'll need to show that if Y is an element of the power set of B, then there exists an X such that G of X equals Y. Okay, so any more than that will essentially mean doing the proof. There's quite a bit more to working it through, but I'll let you play with that if you're so inclined, and I'll put the full solution up after this homework is due. So this last one, number 9, I say is an induction problem. And the reason it suggests itself as an induction problem is because when you read it, it says prove that if a set S is finite, then all of its subsets, so then all of the subsets of S are also finite. Now, this again just seems perfectly obvious. And also, since we're talking about finite sets, it's not obvious that we should have to do this inductively. And in fact, you don't have to do it inductively. It would rely on induction at some level, but there are actually different ways of defining the finite, and there are different ways of approaching this. So this is just one approach that I'm going to talk about, which happens to be inductive. So you'll remember that when we do problems of induction, we need a propositional function. We need to be able to say that there is some actual proposition that can be mapped on to the either true or false that makes some claim. And if we let p to the n just be the claim that every set with finite n elements or for every set with finite n elements, all of its subsets are finite. Okay, so that's just what we want to prove. And so that's just what we want to prove, and you'll remember that we have to prove it with a base case, and then we have to prove it with an inductive step. And usually the base case is pretty simple, and in this case it certainly is, because p of n would be p of 0, so a set with 0 elements, and that of course is the null set, and we know how many subsets the null set has. The null set has one subset, namely itself, and one is finite. So the base case is very easy to prove. Now in the inductive step, it turns out that in this case it's better to do it by strong induction, which means that you are going to assume that Pn is true for all k less than or equal to n. And then what you need to do is show that Pn, right? Show Pn necessarily holds for k equals n plus 1. Now it's not at all obvious how to do this. You just need to come up with ideas and think about it. So I suggest you try that on your own, but if you're struggling, then come back and I'll right now tell you a little more. So what you want to do is think about the set that gets created when you add one more element, or k equals n plus 1, right? So you think about this set, and this set is going to just be, call it S, and just think of it as having k plus 1 elements, right? So when you remove an element from S, you're back to k, and we already know that Pn holds for k. So that might be enough for you. If it seems like it is, see if you can go from there. Otherwise, I'll tell you a little more. So also think about the other set that has k elements, right? So call that, say, S prime, and it has k elements. And then give the element in S that is not in S prime a name, right? Like call it C. Okay, so now just remember what it is that you're thinking about. You're thinking about all of the subsets of S, right? You're trying to prove something about all of the subsets of S. And specifically, what you're trying to prove is that all of the subsets of S are finite, given that S prime and every other set smaller than S prime is also finite. That was actually badly stated. What I mean is given that S prime and all of the sets smaller than S prime are such that all of their subsets are finite. So what you want to do then is remember the proof method of we're involved in here is you need to just choose a subset arbitrarily from S. So you want to just suppose that something, right, call it T, suppose T is a subset of F. And then what you want to show, of course, is that you want to show that T is finite. So now you just have to ask yourself is, well, what are all the things that T could be, right? Because it could be any size. And so you know, for example, that T could be the null set, in which case it's finite. You know that T could be such that it only contains C, right? It contains C and some other stuff. But your hypothesis has told you something about collections of that other stuff. So when you think of the possibility that C is an element of T and that C is not an element of T, and that C is an element of T but not the only element of T, when you think about all three of those possibilities, and those are the only ones, then you'll be able to show on the basis of your hypothesis that S itself has to be finite. Okay, so that's it for this